All right, so I was trying to get into, why the sky is blue and why the sunsets are red. And it has to do with this phenomena in physics known as scattering. It's really the light of a particular wavelength. Remember, wavelength is associated with color, right? Red is longer, blue is shorter. So what happens, like in our atmosphere, sunlight comes in, let's say on a given given day where there's not a lot of clouds. What's happening is the sunlight hits the upper atmosphere, and because of the O3 molecules, right, the ozone, the size of the O3 causes blue light to bounce around more frequently in the upper part of the atmosphere. And so that when you look up and you see the sky is blue, that's why. It's not, some people talk about, this is a reflection of the ocean or so. It's not. That's not it at all. And it's the same reason that when the sun gets close to the horizon from your observation point, as the sun gets closer and closer to the horizon, or rises up for the in the morning, the light is passing through the atmosphere closer to the surface of the Earth, which contains larger molecules. Larger molecules is going to cause red light to bounce around more often, and that's why sunrises and sunsets tend to be more reddish. Reddish. Obviously, sometimes there's orange. It depends on the type of material, the type of gas that it happens to be bouncing around. All right. So what we can do with this is we can look at these interstellar clouds, and we can also determine the composition of the interstellar clouds by looking at the spectral lines. Right? Remember the spectral lines? Remember that demonstration I did in the very early part of the semester, where we looked at the discharge tubes, and we looked through what's called diffraction grating, and then we saw these different colors. We saw the kind of the opposite of this. This is an absorption spectra, whereas we saw what's called an emission spectrum. We saw the colors, where these dark lines would be. We saw those colors. That's just the opposite. That's the light is emitting that, or the type of molecules are emitting the light at those particular wavelengths. So for an emission spectrum, for an absorption spectrum, you have all the colors of the rainbow, that's what starlight is made of, all the colors of the rainbow, but it passes through a cooler gas, and so there's some absorption taking place, and we can actually measure that, and we find that these interstellar clouds, which there's lots and lots of them in the Milky Way galaxy, we find about 71% of the material is hydrogen, 27% helium, and roughly 2% heavier, elements, or what we call metals in astronomy. We even find some chemical compounds, like water, as it says here, some carbon monoxide. I think they've even found nothing really complicated. But they have found some organic molecules. Let me think of what it is. Some like formaldehyde, which is technically organic, but it's nothing. It's not like too advanced or anything like that. All right, so again, here's this idea of scattering. It reddens the light because the blue light tends to bounce around, and the red light passes right through. So that's sometimes called reddening or scattering. Blah, 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 same thing. Just showing you different pictures of the same. Right. So this is just some region, just showing you that there are these regions called dark nebula where you can hardly see through them because you can't see through that stuff in the visible part of the spectrum. And nowadays, of course, well, let me back up just a little bit. They came up with these terms long ago. I don't even like the name the terms, the zones of avoidance. It's like you somehow can't go there or something like that. All that is from our perspective in the Milky Way, where the sun is, where the Earth is in the Milky Way galaxy, there's regions where if we looked like way over here or way over here, those galaxies in the visible part of the spectrum we're blind to those, right? They call them zones of avoidance, but they're just not. We're not really trying to avoid them or anything like that. I mean, it's really that's a bad name. It just means that in the visible part of the spectrum, we can't see those, galaxies that happen to be in these directions. Of course, we can see the galaxies, using "C" in quotes by observing these galaxies in other wavelengths, like radio waves, for example. We can clearly see this stuff in radio. There's of course again the Pleiades. This is also known as the Seven Sisters. It is also called a reflection nebula because what's happening is the blue light is bouncing around inside of it more often, and this is just showing some interstellar gas. It actually gets quite complicated. Like some of these structures are trying to understand these gaseous structures in the galaxy. Some of the stuff is from dying stars. Some of it is from newborn stars. And the newborn stars nowadays, of course, in this time in our galaxy, any new stars that are being born of matter that is, a lot of the matter, the heavier stuff has gone through stellar evolution. So it's made up of heavier things like carbon and oxygen and things like that. All right, so this is just showing you the difference between the emission nebula, or showing an example of an emission nebula. Yeah. We don't really have to get into this too much. If some people, it's actually important talking about these H2 regions. We're not going to get too much into that. This is just showing you that we can, look through this stuff. I think that, this is a map in the radio region, and superimposed with an optical, that is the visible part of the spectrum. Right. This is actually an important wavelength. I just caught my eye here. This 21 centimeter wavelength is actually really important throughout the entire universe, and it has to do with this spin of an electron that will sometimes flip, like it'll go from being a spin-up, has to do with quantum mechanics, it'll go from a spin-up electron to be a spin-down electron, and when that happens, the electron will emit this 21 centimeter wavelength. So that's actually really important, and it helps us to map, where the matter is in the universe as well as in the galaxy, of course. This is the thing about the different. There's the formaldehyde right here. So that's a type of organic molecule that's found. Even ammonia, which is organic. Sorry, this is ammonia, NH3. This is formaldehyde, and this what's called formic acid. And there's even ethyl alcohol or ethanol out there in the universe. All right, but usually we find molecular hydrogen. By far and large, you find H2 out there in the universe. All right, now here's a problem. You might not know it's a problem, but it certainly has been a problem for astronomers for a long time. So you got the spiral arms of a galaxy, right? So let me get to a nice picture. Okay, so here's a picture of the spiral arms of a galaxy. And the problem is that if we don't know, we don't understand fully how the spiral arms form. Now we have some models that try to explain that. Here's one of the leading models. There's many different models, but this one is called a density wave model. And so basically what happens is you have these. So let me back up just a little bit. A density wave is very similar, like sound, for example, is a density wave. What happens with sound when you're making sound? You're compressing the air molecules. If the sound is going through air, let's say, you're compressing the air molecules and stretching the air molecules. Compressing and stretching, compressing and stretching. And of course, it's the same thing that happens when sound goes through a solid or sound goes through a liquid. Okay, so to understand the spiral arms of a galaxy and how they form and how they remain over enormous amounts of time, in the order of billions and billions of years, what astronomers have done is to come up with a model where there are these density waves coming from the core of the galaxy and emanating outward in the galaxy. And so what happens is you have these clouds of gas, right? I mean, we observe that all the time. And then what happens is, as the clouds of gas go through a compressed part of this spiral density wave, then what happens is that you're going to have large-scale star formation and clusters being formed, and so that in those regions, that's where you're going to see lots and lots of stars. So the parts in between the spiral arms are just less dense gas, it's the interstellar clouds, but they haven't been compressed yet. Compressed due to the spiral density wave. Now, here's the problem with that theory, and it's still a model. We don't have a mechanism that generates spiral density waves. So, I mean, maybe somebody will come up with an idea that why are these spiral density waves coming? I mean, if this turns out to be a correct idea, this is the kind of the fun of science is we don't know. We just don't know if this is the right idea. I mean, it certainly would explain what we observe, the spiral arms of the galaxy. This one is a newer model. I'm not that fond of it. It's called the self-propagating star formation model. So we'll run through this real quick. Let's see, how much time do I have? Oh, I only have a few seconds. So I'll probably have to pick this up in the next one. But star formation begins at some random location in the galaxy. As the stars heat up, I'm just going to have to. I'll have to start this in the next video. I'm sorry.